Hello and welcome back to the final section of this course. I'm really excited to finally see you here, having made it all the way through. And now we are talking about neural networks. And this is going to be a really exciting session. In this section, we are going to explore the basic concepts of neural networks. We will look at different activation functions and feed-forward networks. We look at the concepts of gradient descent and backpropagation. And finally, we will build our own neural network using the estimator API of TensorFlow. I can't wait, and let's directly start with our first video of this section, the neural network intro. So in this video, we are going to learn what an artificial neural network actually is and how ANNs work. Let's first try to understand what an artificial neural network is by looking at an example of it. Let's make clear some terminology. What are we seeing here? First is the input layer. Remember the model we built in the last section? Our feature layer object was our input layer. No matter how our neural network architecture looks like, in the end, we will always find our output layer. This is the layer where either the predicted value or a class probability or whatever we are looking for will be outputted. This is the result of our model. What comes between the input and the output layer can have many different forms. No matter how these layers look like, we typically call them our hidden layers. Can you remember the models that we built before, the linear and the logistic regression? They didn't have any hidden layer. All we had was an input layer with our features and an output layer with the linear or sigmoid activation function. In this new example here, we have an architecture where we have two hidden layers. Now, each layer contains a number of units. These units are also called neurons. And to understand the mechanics of a neural network, let's take a closer look how the neuron works. We have seen this picture of a neuron before. Each unit or neuron of a neural network receives a certain number of inputs, where each input has a weight. The neuron then applies an activation function to the weighted sum of the input and calculates the result, which is the output of this neuron. One of the most basic activation functions is a linear activation function, which essentially is the weighted sum of the inputs plus a bias variable b. Let's go back to the neural network. Each layer, except for the input layer, has neurons applying a certain activation function, which is defined per layer. For example, two hidden layers could apply linear activation functions, and the output layer could apply a softmax activation function. For the first hidden layer, we would need to train 8x6 weights because we have 8 input features and 6 nodes. The second layer would need to train 6x6 weights, and the output layer would need to train 6x4 weights, which makes a total of 108 weights or parameters that this network has to learn. And by the way, each activation function has a bias, which we didn't count in, or we assume it is 0, so let's ignore the bias for now, just for the reason of simplicity. So how does the network know or learn which weights to assign in order to get to the desired output values? This is actually a 6-step process, which I would like to quickly demonstrate. Step 1. We initialize the weights randomly using small numbers close to 0, but not 0. Step 2. We feed in the first observation of our training dataset into the input layer where one node represents one feature. Step 3. Now a process called forward propagation comes in. From left to right, the neurons are activated in a way that the weights control the impact of each unit activation. The network propagates the activations until a prediction of y hat is reached. In the first run, the prediction isn't anywhere near accurate. Step 4. The algorithm compares the result of the predicted values to the actual or true results, our training labels, and measures the error. The error is measured systematically using a cost or loss function. Step 5. Now a process which we call backpropagation is setting in. The errors of our predicted values are backpropagated from right to left through the network. This way, the network learns which neurons or weights were most accountable for the error, and the algorithm can update their weights accordingly. This update process is controlled by the learning weight, normally referenced to as the alpha value. Step 6. Finally, we are starting this process again for the next observation in our training dataset. We will iterate over this process until all examples of the training dataset have been processed. Now, depending on whether we update the weights after each batch of observations, this process is called stochastic learning or batch learning. So this whole process will continue until the total number of training epochs that you provided is reached. One epoch is one iteration over the entire training dataset provided. This whole training process might take some time depending on the size of your dataset, the architecture of your model, and of course the computing resources that you have. But at some point this process will finish, and by the end of it the weights of the model should have been fitted to the training data so that the loss function converges or is minimized. And this is what we call our fitted or trained neural network model. Okay, this has been a lot of information obviously. If this was too fast, then I recommend looking at this video again or looking at the different steps. In the following videos, we will look at the individual techniques which are involved in each of the steps in more detail. So it's not necessary for now to understand everything in detail yet. By the end of this introduction, you should at least understand the different types of layers, what a neuron is, and how the training process of a neural network looks like from a high level.